This video is still on the chapter of vectors in vector spaces, and we have been introducing concepts from the chapter of norm or length. So and in the previous videos we introduced the concept of dot product. Okay, so this is the time to introduce a very important concept. The concept of this, I'm going to introduce this inequality called the Cauchy-Schwarz inequality. So if we have vectors u and v in the vector space Rn, this is the inner product, the norm or the length, the norm of u times v, this is an inner product, okay, is less or equal of the norm of u times from inner product times v. This is very important because this is what you learn. You need this for metric spaces, for the beginning of mathematical analysis and all that sort of thing. Okay, so let us prove this Cauchy-Schwarz inequality. Okay, so let us do the proof. Well, for the proof, we are going to prove this stronger statement. So this statement, if you prove a stronger statement than the one you want to prove, that one will be proved. Okay, so this is a stronger statement because the vectors here, they will have n components. Okay, and we are going to prove that the inner product of u times v, the norm of the inner product of u times v is less or equal to the sum from 1 to n of inner product of ui times vi, and actually this one here should be equal. I'm sorry. Okay, it's because this one, at the end of the day, this is how u times v, because u will have n components, right, and v will have n components, so these two, they are equal. Okay, so the strongest statement is this one, that the sum from u of the inner product of ui times vi is less or equal to the norm of u times the norm of v. If one of these, of course that u and v are vectors in Rn. Okay, if either u is equal 0 or v equals 0, okay, or if u or v is equal 0, then what you have is 0 is less or equal than 0, less or equal than 0. Okay, so proved. Okay, so we only need to consider the cases where u is not 0 and v is not 0. Okay, so if u is not 0 and v is not 0, it means that the norm of u is not going to be 0 and the norm of v is not going to be 0 too. Okay, so what we have to prove is this. So we only need to prove this. We need to prove that u times v, the module of u times v, equals so the module of the sum is less or equal than the sum of the modules. Okay, so in order to do not get a heavy notation with ui's and all that, I'm going to normalize these vectors. Okay, so I'm going to divide ui by the norm of u. Okay, and I'm going to call this one x. And in order not to have this, I shouldn't have this one here, right? Because, well, yes, it's okay. It's okay. This is true too. So in order to not to get a heavy notation here on VI dividing, I divide by the norm, okay, and I'm going to call this one Y. Okay, so I will have this one will be X and this one will be Y. And on the top of it, I'm going to use, so this is one first trick in notation, so to speak, and the second one will be, okay, X, where in a certain way X will be a vector and Y will be a vector too, okay? So the second one is, just to remind you, just check the previous video, that U times U is greater than 0, okay? And that's why we proved this in a previous video, right? That U is always greater than 0, okay? And since X is a vector 2, we are going to use X plus Y. Do not forget these are vectors, but I'm going to multiply X by lambda, dot product with lambda X plus Y, and of course using this rule that was proved in a previous video, this has to be greater than 0, because this is a length or a norm, where lambda can be any real number. So we are going to use this inner product, right? This norm, lambda X plus Y squared, because this one times this one, the squared, is greater than 0. Okay, so lambda squared, lambda times X squared, plus 2 lambda xy plus y squared equals, or is greater or equal than 0. So lambda squared x squared 2 lambda xy plus y squared greater or equal than 0. Okay, so I'm going to see all this as a function of lambda. Okay, we have lambda squared here, 2 lambda plus 1, okay, and this, I'm going to treat this as if they were constants, okay, so I have an x squared here, here I have xy, right, the function is a function of lambda, so I have a f of lambda, okay, and 1 is multiplied by y squared. Okay, so I have a function of lambda where this function will be greater than 0, okay, due to this inequality here. Okay, let us solve this equation, try to find the zeros, okay. But this function can only be greater than 0, okay, greater or equal than 0. So let us treat this, or look at this function as a normal. We're going to use the formula to solve second degree equations, okay. So that will be, that's the famous, when you x equals minus b plus minus b squared minus 4ac, right, dividing to a. Okay, let us do that here. So we have minus b, that will be minus 2xy, right, plus minus square root b squared, so 2xy squared minus 4 times a is x squared, and c is y squared, everything divided by a, so that will be divided by 2x squared. Okay, now I just rearranged here, right, because we have 2xy squared, so that's like 2 squared xy squared. Okay, so that's 4xy squared minus 4x squared y squared. Now do not forget that we are working on f of lambda, but we are coming from here, right? So f of lambda has to be greater or equal than 0. Okay, and we already seen for equal. Okay, so this f of lambda has to be greater than 0. So this value here has to be negative, right? Otherwise f of lambda, do not forget this, f of lambda has to be greater than 0. So this value here has to be smaller than 0. So for f of lambda to be greater or equal to 0, it means that this value here has to be smaller than 0. So 4xy squared has to be smaller than 4x squared y squared. Of course, we are going to take this 4 out, and we will get xy squared smaller than x squared y squared. But do not forget that x and y, they are vectors. So what is xy? So at the end of the day, xy, this will be the norm squared, this will be the norm, right? And x squared, so x, the norm of x equals x times x, right? So what we have here is the norm of x inner product with the norm of y. And since at the beginning we used x as the vector u and y as the vector v, we can say that u times v is smaller than the vector u times dot product, of course, the vector v, and this concludes the proof.